Perfect. Yeah, thanks a lot. So my name is Marlene Kretschmer from University of Leipzig, and together with Dept from University of Reading, I'm co-leading a work package in XAIDA on cold extremes or winter extremes with a focus of causal inference methods, which I will here try to briefly introduce to you. So kind of, well, a key approach what we address within our work package, or also within XAIDA in general, is the so-called storyline approach. And the reason for this storyline, or the motivation for the storyline approach, is that extreme events and extreme event impacts have multiple causal factors, and the storyline approach helps us to account for these different factors in a physically consistent way. And this is a figure from a paper from Lisa Lloyd and Ted Shepard. Ted is also on the call, where they presented this idea in the context actually of legal cases. So here, this is a generic so-called causal network or causal graph, where you see the different ingredients of extreme impact. So you can see that there are arrows pointing to impact, which is not only the hazard, so the extreme event, but there's also vulnerability and exposure, of course. And then a hazard also depends on dynamical conditions, so the circulation, atmospheric circulation, as well as regional warming, which are both affected by global warming. And again, there's the role of natural variability, but also greenhouse gas emissions. So in a nutshell, to say it's complicated, and disentangling these different factors, and ideally also put numbers on them and contributing, quantifying the contribution, this is what we aim for, or what, let's say, poses a general challenge in extreme event attribution. To give a bit of a mathematical background, and I will keep it very, very general here, is the difference between correlation and causation, which we, of course, well aware, but this links to this mathematical framework of causal inference. And I personally find this compelling. If you just look at the scatter plot of X and Y, there is a correlation, and we could use X to predict Y, and we could also use Y to predict X. But the difference is what happens if we intervene in the system. So what if one would, for example, climate change lead to changes in one of these factors? And just based on the data, it's basically impossible to tell, because X could be a cause of Y, and Y could be a cause of, or Y could be a cause of X, or there could be a common driver which affects both X and Y. And so, well, yeah, one message here is that data usually doesn't speak for itself. Of course, we have also climate models where we can make these interventions, but then climate models comes with flaws. And this basically introduces, or this is one of the motivation for the so-called causal inference framework, which, again, very briefly here, is about quantifying causal effects from data. And it's actually, it's a very rich mathematical framework to formally include causal knowledge in the statistical analysis. Because what the previous slide, or what I tried to show here, is that just based on the data, it's usually impossible to infer causal effects. But as soon as one has knowledge about the data generating mechanisms, so for example, the knowledge that X is the cause of Y, not the other way around, it is actually sometimes possible to infer causal effects purely based on the data. And this framework is mainly, or it's pioneered by from the mathematician or machine learning scientist Julia Pearl. And actually also, it's slowly entering also climate science. For example, we have a paper in BAMS a few years ago where we introduced this concept to quantify these causal pathways of teleconnections, so these large-scale circulation drivers of extreme events or regional climate changes. There's also a paper where Julia Pearl, but also Freddy Otto, who is also here, was involved on using this causal counterfactual theory for the attribution of climate for extreme event attribution, sorry. And I'm also highlighting another paper here, the one by Lisa Lloyd and Ted Shepard on using this attribution in the legal context. Again, it's framed in the context of storyline, but it's also very much aligned with this idea of using causal networks and using this physically plausible hypotheses of the different causal factors leading to extreme events. This is one example of the storyline approach, an other paper from Lisa van Radon. where she looked at the Russian heat wave, but also the Russian heat wave 2010, but also the European heat wave in 2003. And where basically they used a nudged climate model runs. So basically they fixed the meteorological conditions and run it with in a factual and a counterfactual world. And here you see the evolution of temperatures average over the Russian domain in that summer. Black is era interim, so the observed temperatures. And the blue is the factual world, the factual model runs, and the red is the counterfactual runs. And you can see that, well, first of all, it was well captured, and you also get this very high signal to noise ratios in this context, where one just looks at this counterfactual by fixing these meteorological or the circulation conditions. And the point here is that the probabilistic attribution and the storyline attribution approaches, they are complementary. So they both have their weaknesses and strengths, and they're just also where they allow for different attribution statements. And actually in this paper, they have this this table where they show these different attribution statements. And for example, in the probabilistic case, based on a paper from Otto et al., one can make these statements that the heat wave presented a 1 in a 30-year event, whereas in the storyline approach, it's more of a description and the uniqueness of the event itself. One example from XAIDA, also very general speaking, is that we try to combine these storylines and causal approaches to link the large-scale drivers on the left-hand side in this figure to the impacts. And this is, a conceptual graph here, but we have different large-scale drivers, known drivers in the atmosphere, an ocean, such as El Niño Southern Oscillation, the polar vortex, the quasi-biennial oscillation, etc., which will affect, for example, European weather, which can be then considered as a mediating factor to impacts. And this is one example, and I think Emmanuel is also on the call, and we later have this workshop on energy impact. But we kind of try to bridge from large-scale drivers to the impacts through a causal approach, where we can then again try to quantify different pieces, let's say, of the puzzle using different approaches, but bring it together, hopefully in a concise way. So to conclude, I think the 5 minutes are probably over. So causal inference, well, you can consider it as a tool, but it's in the first place, it's a mathematical framework. And it allows to formally include expert knowledge in the statistic analysis and to infer causal effects. And well, we are convinced this is powerful because when it comes to extreme events and extreme event impacts, there are these multiple causes, and they are also interlinked. So we need to bring in assumptions and also our hypothesis to basically disentangle the different contributions. And we use this in XAIDA, these methods to understand and quantify the role of natural and human factors of extreme events through a storyline approach, next to other methods, of course, which we'll present in the next 2 talks. So yeah, thank you, and happy to take some questions.